Question from October-November 2016, paper 12, question 33. A wire carries a current of 2 amps for 1 hour. How many electrons pass a point in the wire in this time? So I collected all the information from the problem and I did this table. So I is the abbreviation for current, is 2 amps, time 1 hour. I want to know in seconds, is 3,600 seconds. And let me call N sub E, the number of electrons. I forgot to add the charge of an electron, 1.6 times 10 to the negative 19 coulombs. Now, the only two formulas that involved everything in this table is the one for current, which is charge over time, and charge is equal to the number of electrons times the charge of an electron. With these many variables, I'm going to identify the variable that I'm looking for, which is Ne, the number of electrons. How many electrons? Ne. I'm going to rearrange this formula in terms of charge. Charge is equal current times time. Charge is equal to amps times 3,600 seconds. So my charge here is 7,200 coulombs. Now I'm going to rearrange this formula in terms of the number of electrons, or Ne is charge over the charge of an electron. So Ne is 7,200 coulombs over 1.6 times 10 to the negative 19 coulombs. So notice that coulomb cancel with coulomb. So the number of charge, plug in a calculator, is 4.5 times 10 to 22 electrons. That's my final answer, and this is option D. This next question is from May-June 2017, paper 12, question 32. The current in a circuit component is 2 microamps. How many electrons pass through the component each second? This is a data table, and my first one here is current. My first variable is 2 microamps. Now, the selection that I have for answer, we don't have anything with prefixes, so I'm going to expand to this form here to 2 times 10 to the minus 6 amps. So micro is 10 to the minus 6. Next is asking how many electrons, so that is the number of electrons. So this is the number of electrons. And what else it says? It says that how many electrons pass the component each second. Okay, so now our time here is 1 second. And the electron charge is 1.6 times 10 to the negative 19 coulombs. To solve this question, I'm using both equations for charge, current, and time, because that's my data table here. Kind of lead me to these two equations. So I can calculate Q, or charge, using this equation, I times T So my I is 2 times 10 to the negative 6 times 1. So my charge is 2 times 10 to the negative 6 coulomb. Great, but I'm looking for is this guy. So my NE is charge over E. My NE is 2 times 10 to the minus 6 coulombs over 1.6 times 10 to the negative 19 coulombs. Cancel units here. So I'm gonna bring my calculator to show how to type all these in your calculator. So let me start like this. 2 EE negative 6 divided by 1.6 EE negative 19. That's my answer. 1.25 to times 10 to 13 power. So this, I look at my selection. Okay, looks like is A. Question from October, November 2017, paper 11, question 33. The current in the circuit shown is 3.2 milliamps. Here we have a battery, we have a resistor, and you have two defined points here, X and Y. What are the direction of flow and the rate of flow of electrons through the resistor R? So here we have two questions, and I'm going to solve the rate of flow first. So this is my data table based on the information given in this problem. A current is 3.2 milliamps, so milli is 10 to the minus 3. So you need to multiply, it's kind of multiplier. So 3.2 times 10 to the negative 3. The second information is talking about electrons. So every time that I see electrons around a question, even if I use or not, I like to write the charge of an electron. 1.6 times 10 to the negative 19 coulombs. The third information that is hidden here is the rate of flow of electrons. So I know that the number of electrons is NE. But the question is asking the rate of flow. If the rate of flow, so you'll be rate is how a variable change over time. So the time here, I will say is a second. So I'm gonna write second. I'm having this hint that because the way that the answer is presented, the rate of flow per second here is the way that Cambridge does the table heading is the variable, and this dash indicates that what after this dash indicates the unit. So in this case, the unit is per second. So there are two things here that I need to discuss. One is the question is asking the rate of flow of electrons. So I'm looking for the number of electrons, but because it's a rate, the word rate means anything that is over time. So the time here, I'm using second because the table is giving me the hint that you'll be over second. Again, N sub E over S, that's what we are looking for. So this is NE is the number of electrons per second because it's a kind of fraction. In terminology, how you talk about this is the rate, because it's over time, rate of flow of electrons. How many electrons is passing through this resistor? So basically we have two formulas here. We have current, which is charge over time, and we need to have a formula that we can calculate the number of electrons, and that's one that we can use. Charge is equal to the number of electrons times the charge of an electron. I'm going to reorganize this formula right here in terms of charge. Charge is IT. Now I'm going to combine both equations. In other words, if charge is equal to current times time, and charge is equal to the number of electrons times the charge of electrons, so I can say this is charge, so I can make this side of the equation equal to the other side of the equation. Now I'm going to divide both terms by T. Why I'm doing this is because I want to make sure that I have this fraction, which is the one that I'm looking for. So this, I can cancel time. So I is NE over T times E. Now I'm going to divide both terms by E because I want to isolate this guy right here. Okay, so then I cancel those two E's, and what is left is NE over T, which is equal to I over E. I just kind of flip the order of this equation. This is the first, the left side. This is the right side. I just kind of rearrange here. Now I have NE over T is equal to I over E. My I is 3.2 times 10 to the negative 3, and my E is 1.6 times 10 to the negative 19. So let's use the calculator and find the answer for this. 3.2 EE negative 3 divided by 1.6 EE negative 19, and I have 2. The answer here, NE over T, is 2 times 10 to 16. However, the answer, it says per second. Well, we are going to get this. Very simple. So remember, the unit for current here is amps. The unit for charge is coulomb. So let's take a look at the units separately. So A is amps. So the unit for amps is coulomb per second over coulomb. So we can say this coulomb per second, and here you are going to flip like this. So coulomb per second, that's the numerator, and coulomb is on the denominator. So the way that you solve this, so coulomb per second stay like it is, and coulomb now becomes a fraction. So inverse of coulomb, like this. So you cancel this, and amps over C over coulombs actually is 1 over S, or inverse of a S. So we could verify the unit for this is S minus 1. So this is my final answer. Which, oops, I have two options. I have this and I have this. So the direction of flow is going to determine each one I'm going to select. This circuit and this circuit are exactly the same. I just kind of flip a little bit the battery source, the voltage, because I want to show you something. As you see, the X terminal of R is connected to the positive side of this battery. So that will be your X. And the negative side of the battery is connected to the Y. Why I'm doing this? Because the options for direction of flow of electrons states or either X to Y or Y to X. They are two distinguished terms when it comes to direction of a current and direction of electrons. One is how the flow of electrons move in terms of the positive and negative terminal of a battery. Another one is the conventional current direction. A battery is represented by two parallel lines, and one line is longer than the other one. The longer line is the positive terminal of a battery, and the shorter line is the negative terminal of a battery. This is to indicate that the shorter line represents the negative terminal, is the side of the battery with more electrons. So battery is made of a chemical composition and in layers. So one layer of the chemicals, they have more electrons. So that's the one. And the other layers, we have less electrons. So we have a difference between the amount of electrons. That's what is called potential difference. So there is a difference in the number of electrons on both sides. In addition, we have a layer in the battery that works as an insulator that will not let electrons from one side move to the other side, because if this happens, so then we'll have something like this, which means that the number of electrons on both sides are equal, so you don't have a difference anymore. And we need that difference because when we connect a wire to the terminals of the battery and close a circuit, we want that the electrons move through this wire from one terminal of the battery to the other terminal. So electrons are negatively charged and they want to move to the positive side, but they are not going to do because there is a gap here between them. But in a wire, now we are providing a path, the wire is providing a path the electrons can move to the other side of the battery. Now what's going to happen is when you have a wire connected to the battery, so the electrons from this side is going to move just like this. In this direction up to here. So they all the time are gonna move in this direction. So this is how electrons flow. So the flow of electrons. So here, if you are taking notes, this is important. Electrons flow away from the negative terminal to the positive terminal of a cell or battery. Now, the opposite term is the conventional current. So the conventional current, it says the current flows in a closed circuit from the negative to the positive terminal of a battery. So to answer the first question, what is the direction of flow of the electrons? So it's going through Y to X. Y to X, and the option should be this one. So this is the original circuit. So the electrons, not the current, the electrons is going to be flowing through the negative to the positive from Y to X. Question from October, November 2015, paper 12, question 33. Very easy question here. Which unit is equivalent to a coulomb? So you have to go to the formula for current, which is charge over time. So then we have here a coulomb, which is Q, I times time, current times time. So charge is, current is amps, and time is second. So this is a charge, and the unit for charge is coulomb. So unit for Q, which is charge, is coulomb, or C. All right, so this is AS. Question from October, November 2013, paper 13, question 32. The current in a component is reduced uniformly from 100 milliamps to 20 milliamps over a period of 8 seconds. What is the charge that flows during this time? So this is my data table based on the information from this problem. So the current is reduced from 100 milliamps to 20 milliamps. But here say reduce uniformly for this period of time. And what is the charge that flows during this time? So I'm not going to use milli as a multiplier in this case, times 10 to the minus 3, because all my answers are with milli. So I will keep it like it is. To explain how to solve this problem, I want to make an analogy with a car that is driving 100 miles per hour and uniformly, which means at the same rate, reduce its speed to 20 miles per hour and a time of 8 seconds. So what do I get from this? So what do I get from this information? If I'm reducing my speed uniformly, so I can calculate the average speed, which is the initial velocity for this period of time, plus the final velocity for this period of time divided by 2. So we are going to make the same analogy with the current flowing through a component, a current in a component. So a current is flowing, is moving through a component uniformly and is going to reduce its current during this period of time. So this can happen because maybe the component is connected to a variable resistor that is increasing the resistance and also decreasing the current that is flowing through the circuit. Perhaps that's the case. So I'm gonna just use the same analogy to solve this problem. So the average current is the sum of both currents divided by 2, which is 60 milliamps. So to find the charge, what is the charge that flows during this time? Is the current, the average current, times the time. So it's 480 millicoulomb, which is these ones right here. Another straightforward question from May-June 2012, paper 11, question 33. There is a current of 10 milliamps in a conductor for half an hour. How much charge passes a point in the conductor in this time? So this is my data table for this problem, and this time I'm using the multiplier for milli because all my answers here does not show milli. So 10 to the minus, or 10 to the negative 3. Half an hour is 1,800 seconds. And now I can calculate my charge, which is IT. So charge is 10 times 10 to the negative 3 times 1,800. My charge is 18 coulombs. That's the final answer right here.